Okay, so today's warm-up question is asking you to consider a series circuit. It doesn't include the schematic, but if you wanted to, you could sketch it on your paper. Okay, it says that you have 3 resistors in series, that they are 2 ohms, 4 ohms, and 5 ohms, and it says to find the equivalent resistance. And then it asks you to find the current in that circuit if the battery is a 9-volt battery. And then it asks for the total power supplied by the battery. So first things first, if you read a question like this and it's a word problem, I would recommend drawing out your circuit just so you can see what you're doing. So this is basically the circuit that's been described. You don't have to put your resistors in the exact same place, but you do need to have 3 resistors, 2 ohms, 4 ohms, and 5 ohms, and you do need to have it connected to a 9-volt battery because that's what was described by the questions. And so the first question was just to find the equivalent resistance. And for a series circuit, that is the easiest math that we do in here because all you have to do is add them together. 2 plus 4 plus 5 is 11, and so the equivalent resistance of this circuit is 11 ohms. All that means is that this circuit would have the equivalent total resistance and thus the equivalent amount of current to a circuit that just had a single 11 ohm resistor. Okay, so it'd be the same as just having one resistor that's 11 ohms. And you can use that idea to help you find the current because you can just use the total resistance of your circuit along with the battery voltage to solve for I. When you substitute in, that is 9 equals I times 11. Divide both sides by 11 and you get your current as 0.82 amps. So again, make sure that you're writing these down. Obviously, it's a good example to refer back to, but please also enter these as your answers to today's warm-up. And then lastly, we have find the power supplied by the battery. The power supplied by the battery is the total power of the circuit, which means you have to use the total values for voltage and the total value for current. Okay, now again, this is a series circuit. The current's the same everywhere, so the total is the current. So you have 0.82 amps, and then you have the total voltage of the battery, 9 volts, and you just multiply those together to get your power, which will be 7.36 watts. Okay, so these are basically the calculations that we were doing in class together for series circuits on Friday. So hopefully that seemed kind of familiar to you. If not, then you definitely want to go back and look at that stuff again because as we're going through the RA that we're working on, you have to remember the old stuff and then build on it with the new stuff. Today we're going to learn some new stuff because we're going to talk about parallel circuits. Tomorrow we're going to learn more new stuff as we talk about combination circuits, and then Thursday is a work day. Okay, so your next work day is on Thursday, and we did that because we want whoever in your group signed up to build the parallel or combination circuit, we want them to know how to do that. So we made sure to put the next work day after the notes. That's why you don't have 2 in a row. We're going to do notes today over parallel circuits, notes tomorrow over combination circuits, and then you'll have time to build that in class on Thursday. Again, we've already talked about the fact that these circuits can contain the same components but arrange them in different ways. And we talked about the series circuit where our components are all arranged on the same loop. That's what our notes were about before. Today we're talking about parallel circuits. Okay, and it tells us here that both circuits to the right contain the same components, wires, 2 bulbs, and a battery, but the top circuit connects them in series, whereas the bottom circuit is in parallel. If you were to do this, and you could try it out in real life, you'll see it in your house when you build it, or you could look at it in the FET, but if you actually try it out, even though these are the exact same light bulbs and wires and battery, you're going to get different brightnesses in those light bulbs. And the reason why is because we talked about this before. Brightness is power, and you're going to get different power dissipated through each of those bulbs if they're connected in these different ways. So that's what we're going to look at today, is how connecting it in parallel changes some of our math and how it affects things like brightness. Okay, so first let's start with the definition. So a parallel circuit is an electrical configuration with multiple paths for current to flow where components are connected across the same 2 nodes. Okay, and so if you look here, they're literally parallel to each other, and we have this node where these wires meet, And from this point up here, kind of where my cursor is, this node, you have 2 different pathways from that point that it can take. Okay, and then they'll come back together, of course, right here, which is what you're watching in this animation. So this is obviously different than your series circuit, because in the series circuit, everything was on the same loop. But this circuit has basically 2 different loops. They share part of the same path, but then it splits and you have 2 separate loops. And you can follow one of those charges. Just follow it with your eyes, or if you have it on your screen, follow it with your finger. Okay, and they're each going to make a loop. It's just not the same loop. So half of your charges, if the resistors are the same. Sorry, let me preface it with that. If these resistors are the same, half of my charges go through R1 and half of my charges go through R2. Now, if my resistors aren't the same, that's when I have to do the math and figure out how much of them are going in each one. Okay, so again, a parallel circuit is a type of circuit with multiple pathways. It still has the same criteria, closed loops. I put an S on it because now we've got multiple closed loops. And you still have to have a voltage source, which would be a battery, and your components are arranged on different parallel loops. Again, you can add that to your definition if you like. By the way, if you're trying to follow along, I'm on slide 62 right now. You're welcome to open it on your own screen. Again, I told you could test it out in the FET. Okay, this is a screenshot of me doing that. Okay, so I told you that you'd have different brightnesses in your bulbs if you connected them in series versus parallel, because everything about these 2 circuits is the same otherwise. And yet, the bulbs that are connected in parallel are brighter, okay, than the ones in series in this example. And again, that difference that we see is because they're connected in a different way. There's a different amount of total resistance because we calculate it differently. Since they're not on the same loop, we don't just add them together. Okay, so how do we calculate equivalent resistance? Again, we're going to look at schematics instead of diagrams like that in the FET. But here's 2 circuits that have the exact same components. They both have a battery. They both have 2 light bulbs, each of which is 3 ohms. Okay, now if I were to calculate it for the series circuit here on the left, of course my equivalent resistance would be 6 ohms. That's easy. My equivalent resistance on the right is not 6 ohms. So let's talk about how we calculate equivalent resistance in a parallel circuit. And again, this is what you're going to want to write down. It is on the formula chart, but the equation's kind of weird. Okay, the equation is 1 over equivalent resistance equals 1 over R1 plus 1 over R2 plus 1 over however many you have, but it's always the inverse. Okay, and the reason is that because all of the components are on separate loops, if you add another bulb or if you add another resistor, you're also adding another pathway. Okay, so when you add more resistors in parallel, you're adding another path, and that doesn't make your resistance go up. It makes your resistance go down. Because think of it like traffic on the roads. If you're driving somewhere and there's only 2 paths, 2 roads to get there, there's going to be more traffic. If you have the same number of cars, though, and there are 4 pathways to get there, there's going to be less traffic on the roads. Okay, you can think of traffic as your, or the cars on the road as your charges, if you will. And so you're going to have a faster flow of charge, or cars, if you have more pathways to get somewhere. Okay, and thus you have less total resistance. But again, we can practice using this equation to see it mathematically as well. So if we want to define the equivalent resistance for this circuit, let's go ahead and plug it into our equation. It looks like this. Okay, now guys, I'm hoping you can add fractions by hand, but if not, you can type it in the calculator. It's a little tedious and annoying, but you can. However, just as a quick reminder, since it may have been a minute since you've added fractions by hand, you can only add your fractions together if you have a common denominator. Okay, so make sure that I do. All of mine are 2. So this one's easy. But you have to have a common denominator if you're adding them by hand. Now, if your calculator or whatever, it'll do it for you. Okay, but in this case, when you add them, you're only adding the numerators, and your denominator will stay the same. So you get 3 over 2. But that is not your answer, because it's not equal to RT. Okay, this equation is set equal to the inverse of your equivalent resistance, 1 over RT. So once you add them together, then all you need to do is flip your fraction. You need to get the inverse of it. So 3 over 2 becomes 2 over 3, which is 0.6 repeating, or 0.67. And so this circuit up here has an equivalent resistance equal to this circuit right here. It's the same thing as having a single 0.67 ohm resistor. Okay, now if all your resistors are the same, yes, you can use that equation to find your total. But if all your resistors are the same, you can find your total resistance by taking the resistance that you have in the resistor and just dividing it by the number of loops, which is what I ended up doing. Okay, so I have 2 divided by 3. If I had a fourth one on there, I'd have 2 divided by 4. My total resistance would be 0.5. If they're not all the same, that's obviously going to be harder math. Okay, but if they're all the same, there's a shortcut, kind of. You're doing the same thing, it's just a little faster. All right, so I have this. This is the equivalent. This circuit has equivalent resistance to this. And we can use that idea to help us find the current in the circuit. Again, when I solve for the current here, it's the current, the total current that would be leaving the battery in both of these. Okay, and so you're going to use V equals I times R. You're going to go back to Ohm's law. And you can solve for the current because you know the battery's voltage is 9, and you're going to use the equivalent resistance because we're going to figure out the current that is here leaving the battery. I'm aware that it splits in a parallel circuit. It has to, because part of it is going to go down this pathway and part of it's going to go straight, and then another part of it's going to go down this pathway and the rest of it will go straight. There's 3 different loops. Okay, so when you solve for this using your equivalent resistance, you're finding the total current that is leaving the battery before anything splits off. Okay, and so to solve for that, we'll divide both sides by 0.67. 9 divided by 0.67 is 13.43 amps. Questions about that calculation? Okay. Again, here's what is happening here, and this would be a good thing to write down as well. When we add resistors in parallel, our current actually increases because our resistance decreases. Again, I mentioned, think of it like roadways. Look at these 2 animations. The one on the left only has 1 resistor. The one on the right has 3. So if this is traffic, then the one on the left, every single car on the road has to go through that same resistor. Think of them as cars. Look at the one on the right. You can tell just looking at it, those charges are moving faster because there are 3 different pathways they can take. Okay, and so adding more resistors in parallel decreases the equivalent resistance of your circuit. That is a common misconception that students have. It is a commonly missed test question and an idea because it seems backwards to say that adding another resistor would make your resistance go down. But it does if it's added in parallel. Okay, so write down whatever you need to write down. And again, you can see the current represented here by the speed of the particles, how fast they're moving. That's going to be your flow rate. So again, this is kind of summarizing equivalent resistance for series versus parallel. But adding resistors in series increases your total resistance because it's just one more resistor that your charges now have to flow through because they're all in the same loop. However, if you add more resistors in parallel, you decrease the equivalent resistance because as you add that new resistor in parallel, you're also adding another pathway. Okay, and so that causes your total resistance to go down instead of up. All right, so here are 2 circuits. They're both parallel circuits. They both have a 9-volt battery. The one on the left has 2 3-ohm resistors. The one on the right has 4 3-ohm resistors. And the question says, which parallel circuit has the greatest current? We just said this. As you add more resistors, you're going to have less total resistance, not more. And that means you would have more current. So circuit B has 2 times the pathways and thus half the resistance. If you calculated it, and you could calculate each of these. Circuit B will have half as much total resistance as circuit A. Okay, and so circuit B ends up with twice the current. Again, once you figure out that total resistance, your current and your resistance are going to be inversely proportional to each other, so half the total resistance will be twice the current, same as it was before. Any questions about that? All right, let's try looking at series versus parallel. So we can compare 2 series. Now we're going to look at a series circuit and a parallel circuit, and these 2 circuits have these same resistors. They are 4 ohms, 2 ohms, and 12 ohms, and they have the exact same ones. And I gave you harder numbers this time, okay, because these are obviously not the same like the other ones we looked at. Both of these circuits have the same components, they both have the same battery voltage, but they're connected differently. And it says which has greater equivalent resistance. If you're not sure, check it out, do the math. In the series circuit, that's easy math. You just add them up. 4 plus 2 plus 12 gives me an equivalent resistance of 18 ohms. So my series circuit has an equivalent resistance of 18 ohms. Now we're going to do the same process with the parallel circuit. And so this time though, because it's parallel, it's a different equation. It looks like this. Now guys, if you're trying to add this by hand, which I think it's easier to just do it by hand than it is to type it in, unless it's really hard to see your common denominator, and then I'll just use the calculator. But typing fractions in the calculator is tedious, so I just do this by hand. So if you're trying to add fractions by hand, again, as a reminder, you need a common denominator. 4, 2, and 12, easy common denominator here is 12. Okay, so I obviously have 1 over 12 already, but 1 over 4 will become 3 over 12, and 1 over 2 is 6 over 12, and now I can add them. Okay, so you're going to do 3 plus 6 plus 1, which is 10, and so it's 10 over 12. Again, that's not your answer. You still flip it. It becomes 12 over 10, which is 1.2. Again, I think that's faster than typing it in, but if you want to type it in and check your work afterward, you go right ahead. Okay, you should get the same thing so long as you remember to add your fractions correctly. But the total resistance for my parallel circuit, 1.2 ohms, which is less than any of those resistors are individually. So which has greater equivalent resistance? Definitely your series circuit. And that will always be the case. If you have the same resistors and you connect them in series versus parallel, you will have more resistance in your series circuit. Okay, greater current, of course, current and resistance are inversely proportional to one another. So you're going to have a greater total current in your parallel circuit because it has less total resistance. Questions about that? All right. Just as a quick compare and contrast, obviously we just compared and contrast how to calculate the equivalent resistance, but you also need to know just some conceptual things that make these two different types of circuits different. So if you want to sketch a Venn diagram, you can, or you can just write this down in whatever format you want. But in a series circuit, there's only one pathway, whereas a parallel circuit has multiple pathways. In a series circuit, and we didn't talk about this explicitly, but it's true, and you do want to know this, if you were to remove a light bulb or a component, like open a switch or take something out of your series circuit, nothing will light up. Like if you have 5 bulbs in series and you unhook one of them, none of your bulbs are going to light up now because they're all in the same loop. And when you took out that bulb, you also disconnected the loop. Okay, so you'd have to reconnect something to make it the charges flow. So if you have one light bulb burnout in a series circuit and one bulb burns out, they all turn off. Okay, old Christmas lights were like that. There's like Christmas movies where they're trying to find the one bulb that went bad. If you've ever seen Christmas Vacation, for example, their old Christmas lights are like that. The new ones, they didn't do that. And they typically have multiple strands that are all wrapped together now, so that when one goes out, the rest of them still stay lit. But that's true for series. In parallel, you can take one of them out. It won't matter. It's on its own separate loop. Okay, so the rest of your bulbs will stay lit. In a series circuit, your batteries are going to last longer than in a parallel circuit. Your batteries are going to die faster because those charges were moving a lot faster. If you recall, whenever you looked at it, you're going to use up the battery faster as well. They do both need a battery, and they do both have to have closed loops or a closed loop with no gaps. All right, so again, back to our parallel circuit. What changes can increase current in this circuit? Just going back to those factors that affect our current. As a reminder, those are using thicker wires. Okay, so larger cross-sectional area is the other way to say that, but using thicker wires would increase current because it decreases resistance. Using shorter wires would increase current for the same reason, it decreases resistance. Using a more conductive material, so if this circuit was made out of aluminum, like several of yours are, and you swapped it for copper, it would be better. It'd also be more expensive, but it would be better. You would have a greater current because that's a more conductive material. Cooler temperatures can increase your current, and then adding more resistors in parallel. If you add more resistors in parallel, you add more pathways, and that, of course, will also increase your current. We talked about Kirchhoff's rules with our series circuit notes on Friday. I want to revisit those and talk about how those same rules apply to parallel. Okay, so you can see on my screen I have everything on the same screen to just kind of shorten it, but we talked about the loop rule and the junction rule. The loop rule stated that the voltage drops at the resistors or bulbs along a loop have to add up to the battery's voltage. They have the same magnitude. Okay, in a series circuit, that was super easy. Everything's on the same loop, and so your voltage drops add up to the battery's voltage. So if you had 3 resistors, and let's say they're all identical, and you had a 9-volt battery, well then they would be 3, 3, and 3 for your voltage. Okay, your voltage drops would be 3, 3, and 3 because it would have to add up to 9 if they were all the same. If they weren't the same, we had to calculate it. In a parallel circuit though, every resistor is on its own loop. So this is gonna look different when you do your math. Because each resistor is on its own loop, the voltage drop at each resistor will equal the battery. Okay, we'll look at it in a second with an example, but that is how that rule applies because they're each on their own loop. The junction rule stated that the current leaving a node, I just picked the battery, but any node, must equal the current returning to that node, or in this case, returning to the battery. Again, this was conservation of charge. The first one was conservation of energy. In a series circuit, we said that our current was the same everywhere because they're all in the same loop. So the current doesn't split, it just goes through that pathway from the battery, back again, and there's nowhere else for it to go. But in a parallel circuit, if you have multiple loops and you were to find the current through each loop individually, you could add them up and get the total. Okay, and so that's what it says there, and that's what the junction rule states. All right, so let's do some practice calculations with a parallel circuit. Again, if you want to copy this down so that you have an example, it would be a great thing to do because you do need a table like this for your RA, and you need to know how to do the math. It's the same table we used before, which I like because of the way it's set up. We can calculate voltage because V equals I times R. We can literally multiply these two to find V. And then P is V times I. We can multiply these two to find P. So once we start to fill it in, it makes it a little easier to do our math. So again, your first thing you're going to fill in is the values that are in the circuit. Okay, so let's start with the resistances that we see, and then we'll fill in the total resistance as well. Again, my total resistance isn't 6. Don't add them. This is a parallel circuit. It's not series. So when you go to find your total resistance or your equivalent resistance, you have to use the parallel equation for it. On your formula chart, it's labeled equivalent resistance in series and equivalent resistance in parallel. So it says which one is which, and they are labeled. So 1 over 2 plus 1 over 4. Again, I cannot add those as is. I need a common denominator. 1 over 2 is the same thing as 2 over 4. And that I can add 2 over 4 plus 1 over 4 is 3 over 4. Which when I solve for RT means flip that fraction. 4 over 3, or 1 1/3, 1.3 repeating, is my total resistance. And so this circuit has an equivalent resistance of 1.3333. I'm just going to fill it in as 1.3 because I can't fit more digits in my little table. But those are my resistances. Okay, from here, the only other thing labeled in our diagram is our battery, and it has a total voltage of 10 volts. Now you'll notice I filled it in as 10 volts for the entire column. And I explained why when we looked at Kirchhoff's rules a second ago, but let me show you again. Okay, if you look at these charges, again, what we're talking about here is the change in energy. That's what your voltage drop is. And these charges, because each of them only goes through one of these resistors, then that resistor is where your total change in energy happens. And so I have a certain amount of energy added in by the battery. In this particular one, it's 10 volts. I've got 10 volts, and then each of those resistors has to have a 10 volt drop. Okay, because they're all on separate loops. So they're not adding up. Each one is going to be 10 volts. So if you have a parallel circuit, your table will look like this every single time. Every time you're going to have the same value filled in all the way down the voltages. Remember, with series circuits, that wasn't true, but in a series circuit, we have the same value filled in the whole way down for current. That's not going to be true here, okay, because my current's going to split. But I can find my total current. Let's go ahead and do it. V equals I times R. Let's solve for I. Using my total voltage, 10, and my total resistance, 1.33, I can divide both sides to get my current is 7.5 amps. So the total current leaving the battery in this circuit is 7.5 amps. Okay, now this circuit has 2 loops. When you're dealing with parallel or combination circuits, I'm going to strongly encourage you to color code your loops. If you look at my diagram, I have 2 different dotted lines. One of them is blue and one of them is red. Do that on your own paper. When you guys are doing the problem set today, redraw the circuits and draw the colors in, because then you can see where the total current exists and where it's just part of it. I have total current throughout this part where I've got both red and blue, but over here it's just blue. Over here it's just red. Okay, and so I'm only going to have portions of the total. The total is 7.5, so I know only part of it will be through the blue part and the other part will be through the red part, and those 2 parts together have to add up to 7.5. Okay, you can solve for either of them first. It doesn't matter. We have the resistance, we have the voltage, so pick one. Okay, if I want to solve for my 2 ohm resistor first, if I wanted to measure it, I would have to put my ammeter like over here so that it only has the blue dots going through it. Okay, and so if I wanted to find that, I can fill it in my table. V equals I times R is going to be 10 equals I times 2, divide both sides by 2. 10 divided by 2 is 5 amps, and so that would be my current through the 2 ohm resistor would be 5 amps. Now, I can solve for the current through the other resistor because I know that 5 plus that other one has to equal 7.5, so I can find it by subtraction, or I can go back and do Ohm's law again using the values for that other resistor. Okay, either way will work. I'll go ahead and show you with Ohm's law. 10 equals I times 4, divide both sides by 4, and you get 2.5 amps, which is the same thing you would have gotten if you did 7.5 minus 5. Guys, I taught you a phrase yesterday, and you might want to add it to your notes because you can see it right now on my math. Your current will prefer the path of least resistance. Look at the resistances, and look at which one has more current through it. They're not the same. The 2 ohm resistor has more current flowing through it than the 4 ohm resistor. And because the 2 ohm resistor has half the resistance, look at its current. It's twice as much. Okay, so you can also answer these questions proportionally if you want to. But anyway, that is what you're going to see when you do the math. All right, last thing is power. Power calculation is just V times I, and you can just multiply across your table. Again, technically, I just want to mention this. Technically, the voltage at these 2 resistors here is negative 10 because the change in energy is negative there. The battery is positive. If you want to put the negative sign in there, you can. But I do want to mention that because it is a voltage drop. So when you hear me say that, I'm implying that it's negative. All right, back to power. Power is V times I, so you're just going to do V times I for each of those rows. 5 times 10 is 50. 2.5 times 10 is 25, and 7.5 times 10 is 75. I didn't type them in there, but that's what you're going to have. And guys, power determines brightness. We talked about that the other day. So if I asked you which of these is brightest, you're going to pick the one with the most power, which would be the 2 ohm resistor right here, because 5 times 10 is 50. That's more than 25. Okay, and so the 2 ohm resistor has more power. Now, when we talked about series circuits, the one with most resistance was the brightest. That is the opposite in parallel. In a parallel circuit, the one with least resistance is the brightest. But it always comes back to power. If you're not sure, you can't remember which one's which, calculate the power, you'll have your answer. Okay, all right. So looking at this one real quick, we're not going to solve the whole thing, but just answering a couple of conceptual questions. How many loops are there in this circuit? Take a look at it. How many loops does it have? If you're not sure, color code them. There's 1.
3.
There you go, 3. There's 2. There's 3. Again, if you color code them, it makes it easier to see what portions of your current are going through there. So there are a total of 3 loops here. Which resistor has the greatest current through it? Again, if I just look at the 2 ohm versus 4 ohm versus 3 ohm, I don't know how much current is going through each one. I'd have to calculate it, but I do know I can rank them. because I don't know the number, but I know that the current prefers the path of least resistance. And I know that my least resistance, which is 2, will have more current going through it, and that the 4 ohm will have the least, and 3, of course, would be in the middle. Okay, so the most current going through is going to be the path of least resistance. Now, in this particular circuit, if you were asked to calculate the ammeter reading or current reading at like A6, realize that's your total current. But what if you're asked for A5? Okay, you can see if you color code your loops, if you wanted to find A5, you would have to solve for the 2 resistors out here and add them together. And that would give you your resistance at A5. All right, guys. That is it for today's notes. If you want to see another example, there are some example problems on the following slide that you can look at with 3 resistors. Otherwise, you have the rest of the period to work on your assignment, 1202.2 parallel circuits problem set.